Welcome back, everyone. So, today we are going to discuss a very famous topic called attention. It is the part of transformer architecture which made it famous. And we'll try to understand the detailed mathematics behind it and what exactly does it mean when we say we are using attention. Very famous word, but not a lot of people understand it. So, my first question that I'm going to ask you is why exactly do we need attention? So, before we move towards that, you need to understand that before attention, for natural language processing, we used a lot of models like RNN or LSTMs. NLP relied heavily on these two models. They are bad, but why? By bad, what I mean is that they are not as good as the latest transformer architectures. Why? Because RNN and all these models, they read the word sequentially. They read the entire corpus of the text that you have one by one. So you will start with the first word and all the way go up to the last word in your corpus, right? So all these models have some sort of hidden state in them. Let's say HT is that hidden state. The problem with these is HT depends on HT minus one and so on. So to calculate HT, you need to be aware about the values of HT minus one. So the hidden state of the previous layer and so on. So when we reach the end of the sentence, right, final HT, the final hidden state, it is supposed to have the meaning of the entire sentence in its vector. So if you have a sentence of, let's say, T can be something like 1,000 or something, the final hidden state that you have. So we will be traveling like this. So these are all the hidden states and so on. Once you reach the final hidden state, it is supposed to contain the entire meaning of the sentence in a single hidden state vector. But the problem is this presents us with a issue of information bottleneck. So the term is simple, very self-explanatory, but it's called informational bottleneck. So if RNN is given 100-word paragraph, let's say, a single vector at the end, it is supposed to have the entire meaning, but by the word 80 or 50 or anything like that, it must have already forgotten almost everything, right? Why? Because of a problem called vanishing gradients. RNNs suffer a lot in training due to vanishing gradient issue. So the reason why it happens is, suppose you have a hidden state H1 and after that at the end you have a hidden state called H100 and you are calculating the final loss with it, and now you need to update the weights of hidden state 1 based on the final loss that you have calculated. So basically what you want to do is del of j with all the parameters theta, and you want to calculate this gradient to sort of update it using gradient descent, right? But the issue is that due to chain rule, it will look something like this and so on, right? So between this term and the last term, there are around like more than 95. I don't know the exact number. I don't want to calculate it. So more than 95, let's say, hidden states or multiplications that you need to do. So even if one of them is very small, let's say all of them are very big, but one of them is very close to zero, it basically diminishes the meaning of updating or passing down the information from the final hidden state to the first hidden state because the update would be slow. So if you're doing some sort of update, let's say these are the parameters of the hidden state one. Um, these are the new parameters. And for the old ones, we will be doing something like this, right? This term will be very small. So the updates on the parameters of the hidden state indeed will be very small, and we don't want that, right? So then came attention. What attention proposes is we don't want the model to compress the entire info in one vector. So let me just write it down. One thing that they propose, which is basically the issue, the bad thing that we have with RNNs is that the model is compressing the information and one vector, which is the final hidden state vector. Whereas attention asks a question, what if model can look back the entire input sequence at every step? So we have a model, it can look back the entire input sequence in just one step or at every step. This will solve the issue that we have with RNNs, right? Now, before going towards what exactly is the formula and everything for attention is, I just wanted to explore or tell you about an analogy that I uh, prefer. It's called a database analogy. Analogy, yeah, however you pronounce that. Suppose you have a database. In that particular database, you will have three, let's say, things: QKV, query, key, and value. Now, what query will tell you about is it is what are we looking for, whereas key is, let's say, indices or indexes in the data, and the value is the actual content stored. So suppose you have a key value database and there is an entry, let's say apple is 100 grams or something, and a banana is 50 grams. So now if you're just doing a lookup in the database regarding, let's say, apple, so apple is your query, then this apple is your key, and whatever value this returns, which is 100, that will be your value, actual value that is stored. So here we have exact key and query match, and then on the basis of it, it returns the exact values. But what attention is, it is a soft database. Very important term to, understand. Attention is a soft database. So we don't look for exact match between Q and K, and we are just looking for similarity between Q and K. How similar Q, which is a query, and all the keys that we have in our entire database, how similar are they, right? So it is important. Let me just write it down so that we will have a reference to it. So first thing is our query, it does not match with any key. We are just calculating similarity. Second is, um, obviously we are calculating how similar Q is to each K, and then we assign weights, or you can say probability, to each key. So we are assigning a weight to our entire set of keys in our database, or you can also call it a probability score. And based on it, it returns a weighted sum of each value that we have. It will get clear once we look at the equations and try to understand how it exactly matches the conventional databases that we have. Now, this is the most important thing. The formula for attention is we are applying softmax and then multiplying it with V. So there are various components in it. We have Q, we have K transpose, we have a V matrix. We are applying softmax and also dividing it by square root of dimension dk. We will discuss what dk is. Now let's discuss what the um, dimensions of each of these matrix would be. So Q, it will be n cross dk matrix. Uh, it just mentions, again, I'm writing what info do we need. K is also n by dk. The database will tell you that I have this info or I have these keys in me. V is n by dv, and most of the times dk is equals to dv. So for the purpose of this session, we will just consider dk as dv. So it is n cross dk, and it just tells you the actual meaning of the word that we are looking for. I hope the formula is pretty clear. It is very easy. Softmax of qkt divided by root dk, and then uh, we are multiplying it by our value matrix. So what are the steps involved? Let's look at the steps in detail. Step 1, we are computing the similarity. Similarity between what? As we have discussed, between query and k. How do we do that? Just multiply and take a dot product, and this will result in n by n matrix. This is also called a score matrix. S, and each term of s I comma j, it just tells us how much the word I is supposed to attend to the word j. So suppose we have in query, we have a word apple, and keys we have in our database, like let's say banana and London. Now, if we do a dot product of apple and banana, let's say it comes out to be 5, and dot product between apple and London comes out to be minus 10. So what this tells us is that based on our query, apple, the matching keys are banana, and London is not the key that we should be attending to, right? So this is what the score matrix tells us. Now regarding the second step is also very easy, but it requires a mathematical proof to understand why are we doing that. It's called scaling factor, applying the scaling factor, which is basically divided by root dk, this thing. So this is what the scaling factor is. Why are we doing that? So I had studied attention a long time back, but I still did not, explore what is the reason behind multiplying or dividing and scaling the score matrix by root dk. And I just got to know about it today. So let's say we have uh, different kinds of components in Q. So Q is our vector. It is made up of Q1 all the way up to, let's say, QDK. Same goes for key. We have K1 all the way up to KDK. And I'm just signifying them by, let's say, QI and KJ. Or maybe KI again. Now, when what I'm saying is, when dk is very large, when the dimensions that we have in our vectors q, k, and v, they are very large, then qi times ki is also mostly large. This is just an assumption right now. Obviously, it can be very small if all the qi and ki are of opposite signs, and then we are multiplying and then adding them together, they will be very small. So what I'm saying is, when dk is large, there can be a huge variance involved. So suppose each component qi and ki, they are independent random variables, and they have a mean of 0 and a variance of 1. Now, when we calculate the variance of q times k, which is also the variance of sigma qi times ki, we can write it as, we can take out sigma and then just do qi ki, and the variance of qi and ki is 1. So this just comes out to be 1. So I have just skipped a lot of steps, but it is self-understanding. So sigma 1, and we are doing it for dk times, so the value is dk. So if dk is very huge, let's say the dimensions that we are dealing with is 1024, which means we have a very large variance, which is very bad. We don't want a lot of variance in our multiplication. So large variance. So some dot products will be very large, some dot products will be very small. Now, if we give this to softmax, the output of that particular softmax, because remember what we are doing is we are applying the softmax function over qk and then scaling factor. What if the scaling factor was not there? The softmax outputs will be pushed to very extreme. So suppose we have a very large variance and uh, one value after the multiplication of qk is 50, another is minus 50, and most of them lie between the mean, let's say 0, 1, minus 1, and so on. So the highest value 50 will get the highest probability 1, and all of them will get 0. So this will how the probability distribution will look like. This will cause the gradient to become 0 and model will stop learning. So what is the issue? I'll write it down. Gradient for a lot of updates will go towards 0 and model will stop learning. So this defeats the purpose. Now we have scaled our qk by root dk. Now let's calculate the variance of this. The formula for variance is a simple property. The variance of ax is a square times variance of x. So this variance will come out to be 1 by root dk square and variance of qk. We have already calculated that this is 1 and this will be 1 by root dk, 1 by dk. So 1 by dk will be the variance, right? So this will keep, I did a mistake. Variance of qk is not 1, it's dk. And the final answer will be dk by dk, which will be equal to 1. So what just happened is, dividing by root dk, it shrinks the variance down to 1, which will keep our attention scores in a very healthy range to apply softmax over on, right? This is why we are just scaling and multiplying our scores or dot product between q and k by 1 by root dk. Let's move on now. Once it is done, the next step, as you would have guessed, it's applying the softmax. We will apply the softmax to each row of our n by n matrix that came out of q dot k multiplication, and the formula for softmax is, let's say we have xi, it will be nothing but this. So now each row will sum to 1. This is how, when we apply softmax, it assigns the weights to qk matrix, right? Once we do that, it is called attention weight matrix. One of the most important outputs of the entire process. Now, step 4. We have our attention matrix in place. Let's call it W. Now we are just doing W dot V, which is resulting in N cross DK matrix. We can call it as a context matrix. Now, for each word that we have in our corpus, let's say each word CI, what we have done after applying all the steps, CI is the weighted sum of all the value vectors in the sequence. So we can write it as CI is nothing but j equals to 1. It goes from all the way to n. Then we are applying the weights over it, multiplying it by the value vector that we have. So word I, we had our initial representation. Now the word I's representation, it has the context and meaning from the entire sequence. So let's understand it. Let me make a table and let's see what do I mean by that. Suppose q k and then we have v, n equals, let's say, 3. So we have 3 words in our corpus and dk is equals to 2. So each of these, you can say, um word or matrix that we have, they have two-dimensional space that we are talking about. So what q dot k returns is how much a word should attend to a word in our keys. Once we apply softmax over it, it gives us weights. For example, we have attention metrics, and it is the W matrix that we were talking about earlier. It has 3 by 3 rows and columns. This is word 1, word 2, and word 3. Again, word 1, 2, and 3. So just ignore the words. Let's just understand. Um, Actually, they are Q1, Q2, Q3, and Q1, Q2, K3. But now let's just look at the words. Suppose it says that word 1 should focus on word 1 by the weights of zero point 0.1. Remember, this is after applying softmax. Word 2 should be given attention of zero point 0.8. Again, word 3 zero point 0.1, and so on. We can fill the entire matrix by this. Now we have a value matrix. It is 3 by 2. So this is the representation of first word, the second word, and the third word. Let's say we are filling the values some 0 point 0.1, 0 point 0.8, 0 point 0.9, 0 point 0.5. Um, let's just ignore the numbers and their significance for now. But once we are multiplying it, once we multiply W and V together, we will be multiplying zero point 0.1 with zero point 0.1, zero point 0.8 with zero point 0.9, zero point 0.1 with zero point 0.5. So the final resulting matrix will have new updated representation for each of the words. So the first dimension of word 1 will be zero point 0.1 times 0 point 0.1, zero point 0.8 times 0 point 0.9, and zero point 0.1 times 0 point 0.5. Now, what we are doing is we have our weights, we have our contribution in the first dimension of each coming up from each of the words. So what we are saying is in the updated representation of the first word, and we are just looking at the first dimension right now, let's assign zero point 0.1 weight to the first word, zero point 0.8 as the weight to the second word, zero point 0.1 as the weight to zero point 0.5. So the final number that we will have in the first dimension of our representation of first word, it will just simply mean that we are giving the highest weightage to the second word. So again, the representation, the final representation of the first word will have the final, you can say the higher contribution of the second word in it. It is just that. Now we have the updated representation, and you can see it includes the context from all different kind of words that we have in our sequence. Now, after this, the question comes, where do we get our Q, K, and V from? Where are they coming from? So whenever we are training our entire, you can say this attention model, we will have our input X, which will have the, you can say dimension of N cross T model. In this case, let's have it as DK itself. So this is just representation of our entire corpus or vocab into a higher dimensional space. So D can be 5, 1, 12 or 7, 6, 8, something like that. It can be anything that you select. QKV, they are just learned linear transformations of the input matrix. What do I mean by that? Q is nothing but X times WQ. K is nothing but X times WK. V is nothing but X times WV. And all these WQKV, they have a size of D model times DK, and they are updated during the back propagation step. Very important. You should understand how back propagation works. Now, another question comes in is you may have heard of the term multi-head attention. What it is very simple. So the mechanism that we looked at just now, it's called a single head attention mechanism, where whenever we are applying it, that single head attention mechanism can basically try to learn one kind of relationship in the sequence. For example, let's say subject verb. But what about all the other relationships that we have? To solve this, we, at least in the transformer architecture, we apply attention and all the mechanism in mathematics multiple times. To be very specific, h times, where h is what you call head. So if we have 8 head attention, we are applying the same mechanism h times. All of this will be happening in parallel, right? And each of this different attention mechanism will try to understand different kind of relationships that we have in our sequence. So we will have our input x, right? We will have different kind of head. Each head will have their own q, k, v metrics. Then we will have a linear transformation over all of these q, k, v. So you can write it as wi, you can say wi, qi, wi, ki, and wi, vi. So this is a linear transformation. Once we are done across all the heads, we will just concatenate it. We'll concatenate the output of all the h1 all the way up to hh, let's say. And then we will apply a final linear transformation using our output matrix. This will result in n times h times and dv. So uh, this thing is ndv. This we will have concatenation results. So we will have h, right? Now you need to understand how are we getting dv. Dv is just defined as d model by h. So once you multiply it, it becomes n times d model by h times h. So the final dimension comes out to be nothing but n by d model. This is how multi-head attention works in very basic similar fashion. So we will have individual single head attention modules. We will just concatenate together on top of each other and so on, and just multiply them with a final weight matrix output. Weight matrix, you can say that. So there are different terms that we have in self attention, or specifically in attention mechanism. What we have seen is it's called self attention mechanism. It is where QKV that we have, they come from the same sequence. For example, they can be used in the encoder part of the transformer. Then we have something called cross attention. Q may come from some different kind of problem statement, and K and V are coming from one other part of the architecture, right? So Q is from, let's say, first sequence that we have. K and V are coming up from some second different sequence, and they are mostly used in decoder part of the transformer architecture. By now, you may have guessed what are the simple benefits of attention mechanism. The first is they are very highly parallelizable. So RNNs, they have a O and time step problem where we will have to process them sequentially, whereas attention is just a lot of matrix multiplication. That is why they're very easy to train on GPUs, because GPUs love to do attention because they have matrix multiplication, and matrix multiplication can be heavily parallelized. And they are also highly interpretable. So you can just look at the n by n attention matrix where you can understand where each word is attending to which kind of word in the entire sequence. So we have good parallel possibilities that we can highly parallelize it on GPU, then they are also highly interpretable. Okay, that ends the session, but I'll just try to summarize it. So we discussed why do we actually need attention. So before attention, we had our LSTMs where they heavily relied on hidden states, and each hidden state was just the, you can say, product or calculation of previous hidden states. So by the time we reached the end of the sequence, the model might have already forgotten about the previous information or context that we have. That resulted in a problem called information bottleneck. So attention provides it with a solution. It asks a question: what if the model can look back the entire input sequence at every step instead of just compressing the info into one vector? Then we are just looking towards database analogy where QKV are matrices. Q is what we're looking for, K is the index in the data, V is the actual value that we have stored. Now, what I am saying is attention is a soft database where we don't look for the exact match between Q and K. We just look for similarity. And what it returns is, or what it does is, query does not match any key. Database, uh, or basically the mechanism calculates how similar Q is to each key in our database, assigns some kind of weights and probabilities, and returns us a weighted sum of each value. This is the most important formula for attention. Just multiplying Q and K together, scaling it by root dk, and then applying softmax, and then giving us V. Q, K, and V and have similar dimensions, and by dk. The steps are also very similar or very easy to understand. We just compute the similarity. Uh, we apply the scaling factor. We also looked at why are we multiplying the output of Q and K by 1 by root dk because of variance. If we don't do that, the variance of the product will be very high and the model will stop learning. Gradient becomes zero and the learning will stop, and there is no point in looking at this beautiful architecture and making it work. Then we are applying softmax to every row of the n by n matrix. This will result in every row being having the sum up to 1. This is now our attention weight matrix. Then finally we have something called context matrix, which is just the multiplication of attention matrix by V. Then we just looked at an example where we explained what exactly do we mean by, basically when we say that attention just updates the information regarding each word, and somehow it also stores the context and meaning from other words in that entire sequence. We also looked at where QKV come from. They are just linear transformations over the input X. Multi-hit attention is just single attention applied multiple times, concatenated, and you know, uh, multiplied with the final output matrix WO. Then we have the difference between self attention and cross attention. Self attention is used in encoder transformers. Cross attention is used in the decoder part of the transformers. Then we have benefits. Very parallelizable, highly interpretable. This ends the session. Thank you. Have a good day.